push that rock here with some math. Let's extend that last lesson on counting to include permutations or arrangements. So last time we looked at gathering up 5 objects and selecting 2 objects from a set of 5 objects. And we found there were 10 ways to do that. And we said the notation was, hey, you have 5 objects and you want to select 2. This refers to the number of ways to select 2 objects from 5. And we learned to look on Pascal's triangle, and we said that there were 10 ways to do that. Same here, if we have 5 objects and we're going to select 3, the notation is 5 objects, select 3. How many ways are there to do that? Well, there would still be 10. And we listed all 10 here. In fact, I had a little trouble doing it in the last video. It's kind of comical, really. But what I want to do now is think about what happens if we decide to arrange them. So how many arrangements are there? These are just selections. In other words, here, choosing 1 and 2 is no different than choosing 2 and 1. We've selected 1 and 2, or maybe we grabbed 2 first and then we chose 1. It's like you're waiting to find out who the 2 winners of a $1,000 scholarship are. Well, you know, a bunch of you are in a room, and maybe you're 10 finalists in a room, and you've all tried out for this $1,000 scholarship, and you're waiting to hear the winner. If they call one person's name first, you're still on pins and needles because you could still be a winner. And in fact, if they call your name, if you're number 2 and they call you next, then you're happy. You won the $1,000. It didn't matter that they went 1 and 2, except maybe you had a heart attack. But we're going to change the game a little. What if the order does matter? What if we're going to announce a $500 scholarship, and then we're going to announce a $1,000 scholarship, and we're going to do it in that order? Well, then you want to be the second person called. You want the order to be 1 and then 2. You don't want the order to be 2 and then 1. So the order matters. When order matters, we have to list all the change in order. So let's get another color out here. Let's go blue. So 2 and 1 would be different than 1 and 2. 3 and 1 would be different than 1 and 3, and so forth and so on. So all these are different. So 5, 3 is different than 3, 5. 5, 4 is different than 4, 5. 4, 3 is different. 5, 2 is different. 4, 2 is different, and 3, 2 is different. You know, you're thinking to yourself, well, golly, this is easy. There's 2 things in each one of the little deals, so you just double the number, and that's exactly right. You just double it. So we would take 2, multiply it on both sides, and the number of ways to arrange 2 objects from 5 would be 20. So there's 20 arrangements, or what mathematicians call permutations. I hope that can be seen on the video. We'll find out. Okay, no, it could not be seen. There we go, permutations. Okay, so is this what you do in general? If there's 3 things, do you just triple? Well, actually, no. Okay, let's see. Well, let me grab the screen and pull. There we go. Okay, so what is the general way to figure out how many arrangements there are if we know the number of selections off Pascal's triangle? Like here, let's pull off just one of these guys, and let's think about what we could do. Well, I didn't grab that pencil, but that's okay. What can we do here with this guy? Well, we want to find out how many different arrangements there are. Well, there's one of them, but we could also go 3, 5, 4. Oh, but we could put the 4 first, followed by the 3, then followed by the 5. Or we could put the 4 first, followed by the 5, then followed by the 3. And then, of course, we could start with the 5, which would be followed by 3 and 4, or followed by 4 and then 3. Oh, so we didn't just triple. In fact, we sextupled, because since there's 6 ways to do just this one, there's 6 ways to do all of them, so we need to multiply by 6 and by 6. That's on smoke. I wonder how that got there. But so we need to multiply by 6 and by 6. So we get 60 ways to arrange 3 objects from a group of 5. So obviously, what's the pattern here? It's not double then triple. Oh, here's what it is. This wasn't double. this was 2 factorial. 2 factorial, but that's just 2. And over here, it was 3 factorial. Oh, well, that's just 6. So the general pattern is whatever this number is, you have to multiply by that number factorial in order to get all the different arrangements. So to get, let's extend the triangle to another row. This would be 6, 15, 20, 15, 6, and 1. And we want to know how many arrangements, how many permutations of 3 objects from a set of 6 objects. That's the question. How many permutations of 3 objects from a set of 6 objects? Well, you first get the number of selections. So there's 6 objects, we want to choose 3, and that's the number of selections. But then you multiply by 3 factorial. And that's how you do that. Well, we'll finish it off. So 6 choose 3 is, remember this is the 0th row. You got to start with the 0th row, 0th entry, first entry, second entry, third entry, so it's 20, but I have to multiply it by 3 factorial, okay? So that's 20 times 3 factorial, which is 3 times 2 times 1, so that's 6. So I get 6 times 2 is 12, so I get 120 ways to arrange 3 objects from a set of 6. And that's how you do that. I-G-G-Y. Math made simple. That's Simpson Math.